Good morning. I'm Emad Benjamin. I'm a principal engineer at VMware. I've been with VMware for about 10 years, and then in the industry for about 22 years. A little bit about my background. I started out as a C++ software engineer, building various types of applications, systems, and engineering systems. And then about 97, I got involved with Java and almost got into trouble with the establishment that I was with. It was mainly a C++ shop, and they said Java would never take off. Anyway, I've not turned back since then. And so I traveled the world building different trading platforms between 97 and 2005. And then in 2005, I landed at this company called VMware, which I had just recently heard of back then. And then I stayed, hang on, the audio fades in and out. Okay. So, and then the first problem that I was brought in to fix at VMware was an application that did not scale, right? This was, everyone in the software development community had written off that application. I worked on scaling it out, making it independent of the hardware and the operating system. And the next thing I knew is that, wait a minute, there's a whole ocean beneath the software layer called virtualization and infrastructure that's very interesting and that can save your code at the end of the day, even though if the code sucked, right? And so the last 10 years, I've been focusing on how to bridge the gap between developers and infrastructure guys, the glue that's in between. And so I've been also writing about it. I've been spending time abroad. I used to think that here in the US, we have the largest transactional volume that you can find anywhere, right? When in the last 3 years, I've been spending time in China, it blew my mind that just a small community portal, social security portal in a very small province had over 25 million users. That's just one, and there were like about 30 of those across the country. The sort of transactional volume I've dealt with a couple customers to call out New Edge and DTCC, anywhere between 20 million to about 180 million trades a day. So these are significant systems, and when you work with significant systems, it changes your assumptions. Beyond the hello world application deployment pattern, it completely changes it. So let's go on a journey. I'm going to make fun some of the acronyms and patterns and things that are being talked about, microservices, cloud native, 12-factor, all of those things. I like to sprinkle a dosage of reality to all those things and probably get into trouble while doing so, but that's okay. Right. A long week. Something wrong with the audio. It fades in and out. Okay, so it's been a long week. You guys need a break, but the essence of this is that, as I mentioned earlier, as I traveled, I used to think that, when I travel from one region to another, I'm going to see radically different types of problems, right? Systems would be implemented differently, the type of problems would be different, and this would be great. I was wrong. As I went from one country to another, I discovered that the problems were all exactly the same. What's that? Use Java in a certain way, and they repeat problems, right? Anyway, so it was, how did we get here? Before we go looking for solutions or like deployment patterns or infrastructure patterns, frameworks for development, deployment patterns, third platforms, microservices, 12 factors, positioned to save us from the monolithic hell that we are in, right? I like to understand what the problem is first, right? Maybe we should start with that. And then from that, figure out a solution that actually fits in terms of getting us out of the mess. Maybe it's not a mess. So what's really broken? If you look at 44% of new applications being deployed, they missed their SLA. So half of you, if you've rolled out a new application, you've missed your SLA. Your application got written pretty quickly, got deployed, and it missed its SLA. Even though it was brand new code that's leaner and meaner, you deployed it, and half of you missed your SLA. That's okay. That's kind of a tough pill to swallow, but it's okay to live with sometimes. The second thing is that 90% of world applications have 2x more hardware provisioned than what is needed. In other words, half the time you're missing your SLA and you're throwing 2x more hardware at the problem and you're still not fixing it. To me, it means something is really broken. And what's really broken is in the whole mapping of the application footprint or the application components or the application instances onto the hardware. Who is going to tell you how many instances you need of this particular application? Oh, do you need 3 copies of scaled out and they are going to be of 4 gig each? Or do you need 20 of those? And when does that happen? Does it happen at incubation time or does it happen after you've deployed? Most systems it happens after you've deployed and you spend years learning as to how to do that. So I'm gonna switch gears and say, no, it needs to happen beforehand. Even if I'm using a PaaS, it needs to have an incubation time where it simulates and tells me what my application needs, right? Now, whether it's a semi-automated infrastructure as a service that's PaaS minus, or a PaaS plus where you don't care about the infrastructure, I don't want to be surprised at the end of the month with a big bill. Now, essentially, these silos that we all live with are causing this problem. Business has a certain notion of the importance of the application. It gets mapped to business analysts and application developers, and they write the code, and they use one set of language, both natural language and computer language. So the signal is lost. And then the signal is lost again as it's mapped from development to infrastructure. This is why we're in the mess that we are in right now. 2x more hardware and we're still missing our SLA half the time. Something is completely broken. And so I just recently attended a CIO forum and I was trying to prepare for it. And the main title of the CIO forum said that CIOs in 3 to 5 years' time want to get out of the infrastructure business. And I'm thinking to myself, at the end of the day, no matter how much software we write, no matter how many hypervisors we have, how many software layers, at the end of the day, you still need hardware to run on. So what does it mean for CIOs to get out of the infrastructure business? Oh, maybe they'll use some cloud, or they'll use some PaaS. Okay. But is it really this problem that they're trying to get out of, right? The problem that they're trying to get out of or get away from is the 2x amount of hardware being over-provisioned and missing their SLA half the time. This is where CIOs are getting into trouble. They're spending 2x more on hardware and still missing their SLA. That's why they have to go and find a new job after a while. They're not, when they're saying we want to get away from infrastructure, what they're really saying is that when I deploy to a PaaS, I want my problems to go away. I don't want to pay 2x for it, and I don't want to miss my SLA. So we need to fix this, and in this talk, I'll be focusing on the various deployment patterns that our industry is seeing these days, right? It's not always just about the third platform. We have a ton of second platform that still needs babysitting and is going to be with us for a long time. All right, so let's drill a little bit deeper here. Here's a typical IT, right? We have some business sponsors, the VPs are there and so on. The CIO kind of sits, says this business application is really important to us, and then a bunch of business processes are mapped, then those processes are mapped to IT services, then eventually it gets down to, hey, I need this app to provide this functionality, I need this data, and I need this ops infrastructure. The corner of the world that I like to identify right there is the platform engineering world, where in the next 3 to 5 years, more platform engineers will actually be anointed. What is a platform engineer? If we took a triangulation or an intersection of perfect skill set, this is somebody who's got some developer background, some infrastructure background, and some application runtime background. It turns out the thing that's highly contested, that no one wants to own this hot potato, is the application runtime right in the middle. What happens is, as developers, we took a half a guess at the Java heap size. We say, hey, we think the app needs 4 gig. Do some testing, and don't bother me because I'm off to the next 5 lines of code that I've been trying to figure out for the last week or so. So don't call me. So the infrastructure guy or DevOps guy, whoever's doing operations for you, is sitting there, doesn't really know how to play around with JVMs and size them, and doesn't really know what you wrote, knows a little bit about how it gets deployed and so on. So no one is really owning it, you know. There's assumptions that, you know, the developers own it, and they don't. There's assumptions that the DevOps or the ops guys own it, and they don't really have the background to own it. So we need to fill this gap, and the only way to fill this gap, and we've done this with many customers, for example, at NewEdge, is a trading platform, is Gemfire running on vSphere, and their original DevOps team became their new Java DBA team that's got Linux background, some Java development background, and you know, just enough virtualization background to be able to babysit the environment and take care of everything that it needs. Stop, start, size, reconfigure, and redeploy the entire trading platform that's made up of Gemfire and vSphere. You can't ask your developers to do that all the time. Sure, they can be involved if there's a bug and, you know, kind of own it all the way through, but at some point, you need to create that specialization, and that specialization I call out as platform engineers. So last year you heard about microservices, this year you heard about cloud native, you know, every year you'll hear about something. So what does it mean to say cloud native? You mean it's platform engineered. You mean it's going to take care of all my problems. The word native and cloud native assumes that it natively takes care of things for me. But is that completely true? It's not. It doesn't matter how much of a cloud native implementation or robust cloud native implementation is, you have to intimately understand the platform engineering aspect of your application, how it needs to be mapped onto the infrastructure it uses. Now, you can go from a private infrastructure where you actually intimately understand the mapping to a PaaS provider where, you know, the infrastructure underneath is opaque, and that's fine. But at least you understand that when you get your bill at the end of the month, that you don't need 100 CPU cycles, because you know internally you ran it with 10 CPU cycles. You need to understand that much, otherwise you're going to be charged through the roof and get into trouble. All right. So typically, he's a typical organization, right? I mean, you could literally draw almost every enterprise into these kind of sub-platforms. You got some sub-platform servicing external users, another platform servicing internal users, and then a platform that copies data in between, your data platform, right? Drilling down on every one of these platforms is made up of some portals, some middleware, database, might be an in-memory database, some data store, and some batching systems. Does this sound like something you guys deal with every day? Yeah? I mean, it's really that simple, right? What I like to do in every design, and we did this for trading platforms as well, is actually start right at the top. I go to the load balancer, and I study it in terms of the transactional volume. I also study in terms of the transactional patterns. If I have a microservices deployment of 100 things that keep talking to each other, then I say, oh, wait a minute. Maybe they need to be part of the same deployment unit in the same runtime space, and then we scale up. And I'm going to show you how to do that in a minute. And if somebody's selling me third platforming thinking, I don't want to rewrite my public portals. It took me years to put it together. Maybe my middleware can move in that direction because it's kind of self-contained and it has all the business logic that can be easily changed. Okay, so I can start to introduce third platform and microservices thinking at my middleware layer and slowly move the environment that way. So this is where I say, it's not always about the third platform, it's about how the second platform can use the third platform. And some of the marketers have gotten really funny, and they start to say, oh, wait a minute, maybe there's the 2.5 platform. All right, come on, guys. This stuff has not changed that radically. It's just what we refer to and call these things changes. Okay, so I'm telling you about this platform engineering concept. I'm not trying to create something new. It's about people, process, technology, and infrastructure, try and build robust platform engineering. That sounds to me like DevOps. Yeah, it kind of is DevOps, right? So in 2006, you had the Y Slow team at Yahoo, you had the site reliability engineering team at Google, and at VMware we had our own reliability engineering team, and we were actually experimenting with the concept of take a developer, put them in operations, catch all the bugs, fix them, get the reliability up, and so on. And in 2009, sometime around 2009, the concept of DevOps was officially established, right? And the founding principles of DevOps were about reliability. What has happened to DevOps in recent years is it's become all about automation. Oh, no, you need to automate this, you need to automate that. And slowly saw a lot of the DevOps engineers not have the right reliability background, understanding tuning of applications and so on. Some of them still do, but we need to get back to basics in terms of like, wait a minute, there's a platform engineering concept here that talks about understanding the deployment pattern of the application, how many components, how the components interact, and because of that interaction, it dictates how you actually blueprint the infrastructure. All right. So obviously in an hour and a half, I can't cover everything to do with these platforms. So I cherry-picked the single most important rules that you need to know whenever you're dabbling with these type of platforms. At the end of the day, they're all Java platforms, right? And if it's .NET, then you're not at the right conference, right? So maybe some of you are dabbling with .NET. All right. So rule number one, the most misunderstood rule is the sizing rule, okay? Understanding JVMs and their sizing. Here I'm going to take a virtual machine. It needs some memory space for the operating system. And then I have the Java process. Inside the Java process, I have the heap. Okay? Heap is made up of initial heap and max heap, right? And you always set the initial heap equal to the max heap. Just don't bother not doing that because the savings are not worth it, okay? Outside of the heap, you've got the Java stack and permgen area in Java 8 that has moved into the heap, and then the other mem section. Now, the other mem section is used for socket communication, the internal JIT information, and so on. It's a fairly insignificant area in terms of size. If you have products, and not to pick on any vendor products here, some products bypass the heap and go directly to the buffer space, direct buffer. That's being allocated in the off the heap section over here. But what I want to highlight is that most developers, I myself a developer, when I first got started with this, I knew a lot about the heap. I didn't know much about off the heap section. We tend to ignore off the heap sections, like, oh yeah, whatever. But it's a significant portion of the sizing problem. So let's put an equation to it. So if I'm sizing a system, I'm going to need some guest OS memory and JVM memory. Now, JVM memory turns out to be the heap, the perm size, the number of concurrent threads times the stack, and other mem section. Now, here's a common problem I found in the field. Customer increases the amount of memory that's available to the VM or the operating system, but they don't touch the heap size. You need to actually allocate the heap size, to increase the heap size, right, in order to benefit. That's an obvious one. But here is the not so obvious configuration. They'll increase the number of CPU cycles, so they'll go from 2 vCPUs to 4 vCPUs, but not change the max threads. And let's say if this was a Tomcat container, the number of concurrent threads basically is the max threads, right? They don't touch that. And then they'll say, well, I can't pump any more transactions through. That's because you're actually limiting, you're bottlenecking how many transactions you can go through. You need to increase the max threads. If you went from 2 vCPU to 4 vCPU, you need to double your max threads at least, right? Another problem I find is that people don't do the math right in terms of if you have multiple JVMs running on an operating system, you need to have an N factor in this, multiply out the JVM overhead. So let's look at a real example. Here, I'm using a 4 gig example. Now, let me kind of just step back a little bit. I call the 4 gig the new 1 gig. And if you guys follow my vmjava.com blog, but I talk about it there. 4 gig is the new 1 gig. Why do I say that? Well, in 32-bit days, the 1 gig was so popular because that's the single contiguous space you could get from a 32-bit JVM, right? It turns out a lot of systems got written back, a lot of Java systems actually got written back about 10 years ago, and they got slowly changed, but their deployment pattern didn't change. So in other words, if you had an application that required 100 gig worth of heap, you'll still find like 100 JVMs running the application, even though it's running on a 64-bit JVM. Well, let me explain something further. The 4 gig is a natural 32-bit space. So in other words, inside the 4 gig space, it's 2 to 32. It's automatically compressed down to 32-bit. Now, why do we do that? Well, when you go from 32-bit to 64-bit, the pointer doubles in space, right? So if you had no compression, you take a 1 gig JVM app and deploy it in 64-bit, all of a sudden you need 2x amount of memory. Well, JVM vendors were not stupid. They knew this was coming, and they created compression algorithms. So the compression algorithm is automatic and it's free. By free, I mean there's literally no overhead, very minimal, up to 4 gig. So if I had an application that had 100 gig and 100 JVMs, I'll be saying like, wait a minute, I can run that with 25 JVMs and 4 gig heap space on each. I just got rid of 75% of my monitoring agents. I just got rid of a substantial number of CPU cycles and so on. Later, I'll show you a performance chart. So when I go around tuning these systems these days, it's difficult to ask a customer to say, hey, I can run your system in 3 JVMs. That's plenty HA. And by the way, it's 90 gig JVMs on each, right? That's kind of like, if I was running the system and I was the admin, I would do that because I know what needs to be done. But it's pretty easy to say, hey, can you go from 1 gig to 4 gig? Most will say, yeah, sure. Well, you just had a 75% saving. All right, so I like getting rid of 1 gig JVMs. They're problematic. And they're problematic for many reasons, too. Another reason is this. If you look at the 1 gig heap space, only a third of it, and sometimes even 10% of it, is the young generation. So in other words, if you've got bad response time, it's because you got 1 gig JVMs, right? All of the initial activity is inside that young generation. So yeah, getting rid of it is important. All right, let's get back to sizing. Here, I'm sizing an application with 100 threads. The default stack is 256K on Linux. Now, if you're on Windows, the default stack is 1 meg. Now, later on, I'll show you categories of applications, right? So if you have an in-memory database, we tend to dabble with the stack. We increase the stack. But if you have a web app, what I call a category 1 type of application, we don't touch the stack, right? Now, if you've got a Stack Overflow situation, you've either got reflection code that's not terminating properly or recursive code that's not terminating properly, and you need to go fix that, because no matter how much of a stack you give it, eventually it'll overflow. But what I have seen over the years, obviously a lot of, so frameworks are great, right? But they're not free. They come with a lot of reflection code, and reflection code tends to beef up the stack usage. So you may see, stack sizes increase, and I've dabbled with stack sizes as much as 4 meg stacks for like in-memory databases, and for web apps, never more than 1 meg unless there's a specific problem. All right, so it turns out that when I've got a 4 gig heap, what I'm talking about in terms of how much that Java process uses is about 1.2 to 1.25 of that heap. So it's really 4.5 gig. So all of your Java systems are missized by that factor. There you go. That's like a quarter of your problems. Now I need a 0.5 gig for the OS, and that's 5 gig, basically. So I like to summarize that. Basically, you can get away with a 1.1 multiplication factor, 4 times 1.1, or up to 4 times 1.25. That's the range that I've seen. If you have a situation where this range is not good enough, then there's a script that I run. I can pretty much, there's like 2 products that do that, and I won't pick on them. They're in the in-memory database space. That's because they're bypassing the heap and allocating direct buffers. You no longer need to do that. The JVM algorithms and heap space allocation has gotten really, really good. All right. Now, when you're sizing, another thing I want to say, when you're sizing systems, how do you actually size a system? Do you size it based on CPU utilization or heap utilization? You always size it based on heap utilization because of the inherent structure of the language, Java. Heap allocation is paramount. It actually uses more heap, and the way we write applications, we use more heap, right? Because we don't get rid of it. We wait for the engine to get rid of it, the Java virtual machine to get rid of it. That's your limiting design factor. CPU comes later. Actually, JVMs do pretty well with CPUs in terms of CPU utilization. So I always size systems. I get on a phone call with customers, and first thing I ask is, okay, is this the same application we're talking about or different applications? How many JVMs do you have? What is the heap size? I tally it up. I look at the usage patterns in terms of like the call paradigm, what's calling what. And I quickly crunch through the math just based on the total heap. So if it's a 400 gig system and it's 400 JVMs, then I know what I need to do with it, right? I can compress it down to 100 JVMs or 4 gig each. That's the first thing I could do, right? And then there are other things. But I use heap as a guiding principle, a total aggregate heap across the system. Okay. tuning is a multi-tiered concern, okay? I'm a big believer that actually when we fix a problem in one tier, we just shift it to another tier in terms of the next problem that we've introduced. And this is important to understand. If you look at the 4 governing tiers of most applications these days, you always have a load balancer. There's some sort of web server tier, a Java application server tier, and a database server tier. And there are variations of this, right? In the middle, you might have middleware that's running around. A database tier, you might have an in-memory database that's talking to a relational database, and so on. But essentially, when I'm navigating systems, I'm structuring my analysis questions according to these tiers. I go talk to the load balancer guys. I find out how many pools they have, and so on. I go to the web server guys. Hey, how did you size Apache? How many processing? What kind of size? I have equations on how to size Apache processes. We won't have time to go into those today, but they're fairly well documented. And then I do mapping. I say, okay, well, actually, let me go to the next slide that talks about it. So let's drill down a little bit further. So let's say I have a pool, right? I have a load balancer. It receives a lot of traffic. So the first thing you need to know is how much traffic you're receiving, right? Let's say you get 1,000 hits. Now, of those 1,000 hits, maybe half are HTML lookup, right? Now, assuming here you're handling HTML. There's no other content provider that's handling it for you. But if there is, you need to make that assumption, right? And figure that out. Then if you've got 500 HTTP threads being requested, how have you done your Apache process sizing? And how many OS instances and VMs do you need, right? You'll find most of it is being guessed by a Linux admin who happens to be a part-time Apache guy. Problem begins right there. Okay. So the call is terminated, returned back and terminated, off to the user, and they see the page, and it's done. Now, the other half of the calls are dynamic calls, right? These are going to be Java bound. Now, notice here I'm using a secondary pool, okay? I'm rebalancing the secondary pool. Now, most systems that I've seen actually don't have the secondary pool. They'll go straight, once they've load balanced to the first over here, they'll just go straight to these instances. Sometimes they'll use different load balancing mechanisms there, but most of the time they're hard-coded to one of these. And that's a disaster because you could have a Java application container that have failed here, but Apache doesn't actually know how to communicate that to the load balancer. So the load balancer keeps sending traffic, but your transactions are not completing. Yeah, your system is up, but it's up and useless. For those users who happen to be unlucky to hit that application container. That's one issue. So what I like to do is load balance it again, and there's actually next to zero overhead in using a secondary pool, because this balancing doesn't actually cross the tier. It happens to come back to the load balancer pretty quickly, and then the load balancer offloads it to the next pool in its configuration. Now I've got 500 threads hitting my Java tier. Oh, 500 threads. Do I have 2 containers with 250 threads each? Or do I have 5 containers with 100 threads each? Who makes that decision? You need to sit down and calculate that out. There's a cost to it. If I'm going to use 500 containers, well, my containers licensed or not? Maybe they're not. What's the CPU usage pattern if I use 5 containers? And wait a minute, if I use 5 containers from day one, remember, as I scale out, I'm probably going to scale out many times over and over again, so I'm eating up the cost pretty heavily, pretty quickly. Maybe I need 3 containers, right? Anyway, so that's one decision to be made, and so on. And then database connections. So there's actually a relationship between the number of threads that you have in your JVM and your application server container, and the number of database connections. Now, in a perfect world where we were all supernatural developers and our code never deadlocked, you should see if I've got 500 threads, I should not need more than 50 database connections. You talk to a DBA, might even tell you you only should need 10 connections. But anyway, that's a DBA problem. Here's what I'm finding in systems around the world consistently. There's a one-to-one relationship between the number of threads and database connections. In fact, whenever I have a deadlock situation, in order to keep production going, to try and defer the deadlock or the timing up, so deadlocks is basically a timing opportunity. In order to defer that, if I have 500 threads, my database connection will be 501 plus. So I always have to have one extra connection in order to delay that lock. So then I size it to that, give them a little bit of breathing space, little runway, and then go back and look at the code and resolve the deadlock. But ideally, it shouldn't be like that, but it is. Now, some customers will say, you know what, this is the way it's been. We're just gonna stay with it. Okay, let's keep going. All right. So I think just to summarize a little bit, each tier decision and tuning has an impact on the next tier. Don't assume, and there's always a race to assume that it's a Java heap problem or a GC problem, and you go try and fix it at the Java layer. It's multi-tier. You need to walk through all of the tiers. We talked about using separate load balancers. Okay? Now, I talked about how the public portal has a load balancer out front, and then a public portal talks to middleware, right, which has another load balancer pool. But if my middleware, and I've seen this situation, let's say my middleware talks to another organization's middleware or another middleware set, I'll use a different pool for that. And the reason why I do that is because I want to know what the transactional stats are for that side of the house. I want to be able to tune it differently and scale it differently. So don't be shy to use multiple pools to make an organizational blueprint of the call paradigm of your application. All right, understanding workload categories. This is the single thing that is overlooked and misunderstood. Not to pick on anybody, even some PaaS providers don't understand this really well. There's this notion that best practices should be the same for everything. If I have an in-memory database, it should be sized the same way as a web application. Really? Well, what if I have a 1 terabyte in-memory database? Does that mean I have to have 1,000 JVMs of 1 gig each? Or 250 JVMs of 4 gig each? No, that doesn't make sense. It makes sense for web apps, but it doesn't make sense for in-memory databases. And we'll go through it. So I like to call out category 1. 80% of what we do is category 1. It's web apps. It's what they call these days monolithic. And the notion monolithic being, big, ugly, useless, and so on, but hey, it makes money, right? It's driving revenue to your systems. It's not going to go away. So we need a recipe for success in terms of how to tune these. And if you look at some of the stuff I've documented, I have best practices for these type of platforms, right? Now, these type of applications, so one of the challenges with these systems is the tenancy, right? The tenancy problem. In other words, you have to service different applications. And the reason why you have too many JVMs is because you've got 100 different apps that are from different organizations. They have different life cycles and so on. Well, the JVM is not multi-tenant. I'm not going to talk about multi-tenant JVMs here. That's coming. But today, the JVM is not multi-tenant. So my tenancy context is really the JVM, which is too coarse. I mean, it's too expensive, but that's all we have. This is one of the challenges with microservices, right? Microservices, and I was going to avoid talking about microservices, but yeah, anyway. The problem with microservices is that you deploy 1,000 microservices, and if your runtime paradigm is a JVM, you are in deep trouble, right? But what if the JVM was multi-tenant capable, and you said, you know what, I just happen to have 100 tenants, so take 100 of these and put them in one process space, one JVM. And I can stop each one and redeploy independent of the other, even though they're in the same JVM. That's multi-tenancy. Don't have that today. So these Category 1 applications suffer from that misdeployment. Question? I thought you said you were going to leave. Yeah, so did you guys hear that question? Isn't that a Tomcat container with multiple wars dropped in? Yes, it is, but those wars are not completely independent. I can write 2 lines of code and I can suck out all of the objects from the other war file. Remember, tenancy means a guarantee that there's a certain security boundary, redeploy the war without causing the other war to go, you don't have to dump all of the cache from, let's not get into all of the through with doing that. So no, so the answer, it's not, it's something different. By the way, you can ask me questions anytime. So, all right. So Category 1, go ahead. What about containers? Which containers? Like Docker containers? What about them? Okay. Can you use, no. So the issue with that is you still have, so you can use containers to do the isolation, but you still have the coarse JVM, big JVM overhead for those microservices. So that doesn't really solve the problem. Although you could use that. You could use containers to do that. It's not a complete solution. Because you can actually still reach from one container to another container if they have a shared runtime space, like a common library or something like that. So it's not completely isolated. But you're right, you could use containers to solve this problem. You could use virtualization to solve the problem. All of those things are not as powerful as a multi-tenant JVM. So the challenge becomes like this. I've got a 2-socket server. It's got 16 cores on it, 16 CPUs on it. It's got, 256 gig worth of RAM. And I decide to say, hey, I'm going to deploy 4 gig JVMs on this architecture. Well, 256 divided by 4.5, half for the overhead, is about 57 JVMs. 57 JVMs on top of this type of hardware, quickly I find I'm CPU bound because I've got 57 GC cycles. So if they happen to all peak at the same time and I'm unlucky, I'm in trouble. So then I bought too much memory for this server. I'm going to swap the amount of memory that I bought and go buy more CPU. So this happens at design time, right? At design time, you need to decide that, wait a minute, we're not going to spend that much money on memory. We're going to go get different servers. Now, if you deploy in a PaaS, you don't have to worry about these type of things. But on day one, when you deploy to PaaS, you give them a requirements document and you say, can you comply with these restrictions? Right? Can you tell me how many CPUs I'll use in a month? Don't tell me at the end of the month. I don't want to incur the charge at the end of the month. Tell me ahead of time. And if you're not equipped this way, it's your fault. You're just gonna make a CIO lose their job. Maybe that's what you're trying to do. But anyway, you get the point. So Category 1 is typically web apps. Hundreds and thousands of JVMs, very small JVMs. They're CPU bound. They're problematic in terms of being able to deal with them. There's too many monitoring agents and so on. I like to consolidate them as much as possible. If there's 20 copies of a JVM that's running the same app, I like to go down to maybe 5 JVMs. Okay, Category 2 is in-memory databases and messaging systems. your middleware. Remember, for the most part, your middleware is really one tenant, unless you're running multiple middlewares, right? But it's really one tenant. It's servicing your entire organization. So it's really one big app, right? And you replicate that across. You want to see as fewer JVMs as possible because you're trying to return a transaction as quickly as possible. You don't want to deal with distribution issues, network hop, latency, and so on. It's latency sensitive. Typically, what I want to see is fewer JVMs as possible on these systems. So the trading platform that I referred to at New Edge, initially, it had to service 1 terabyte of memory, right? So somebody had read one of my best practices, which is, up to Java 7, remember I talked about 32-bit compression, 64-bit down to 32-bit compression? Well, in Java 6 and 7, that's only effective up to 32 gig of heap space. And Java 8 is higher than that at 64. So somebody had read that and taken it verbatimly and said, oh, okay, 1,000 gig divided by 32, roughly it's about 30 JVMs, blah, blah, blah. So we need 30 JVMs. Well, there's no way that system was going to scale. There's just too many network hops. So we don't care about memory compression in that case because we had plenty of memory. And we ended up with 8 JVMs of 90 gig heap each. And they're doing 20 million trades a day. So that, to me, is a different category of a system. Could you use this type of pattern for web apps? Yeah, you could, but then 90 gig worth of heap space, you have to be like a top 10 provider in terms of transactional volume to be able to fill that up. You're not going to be able to fill it up because you got 100 apps. You're not going to do that 100 times, so it doesn't make sense. So category 1, 4 gig is your new 1 gig friend. In category 2, less than a dozen of a JVMs is the rule. Almost, yeah.
So you said the category 1, the 4G
Yeah.
is the new 1 GB.
Yeah.
Does it apply for small applications? I mean,
Yeah.
if you're just putting in 4 GB, it will take more time for the full garbage collection. And, and also it's CPU bound. So 1 GB probably is better for small applications, right? Or maybe 2 GB. How would you,
Okay, so I think I'm hearing kind of multiple questions there. So the question was, let me repeat it for the rest of the audience. Maybe your app doesn't, and I'm paraphrasing here, so correct me if I'm wrong. Maybe your app doesn't need 4 gig, and 4 gig might have issues with garbage collection cycles. That's the myth. The problem is this. Eventually, you're going to get to 4 gig. So you roll out an application that today doesn't need 4 gig. But if you compare the infrastructure overhead and the JVM overhead and the CPU cycle overhead of a 1 gig JVM compared to basically a 4 gig JVM, the overhead is about the same. It's like once a JVM is launched, the allocation of the additional heap space is almost free. Now, there are caveats to that. I won't get into it now. Like, if you're using always pre-touch or if you're touching all of the heap spaces, it takes longer for your application to launch, right? But remember, startup time compared to runtime performance, I always would prefer, I don't care if it takes a little bit longer to start up, because guess what? I've got 100 copies of this thing. I'm servicing transactions. This thing can take as long as it wants, right? As long as it's not hours and hours. But if it goes from 1 minute to 2 minutes, I don't care. When it's ready, I'll put it into the pool and start sending traffic to it. Versus, having response time issues with the 1 gig and so on. So really, look, I go through this all the time, and every time a customer has gone against that, they've eventually just gone to 4 gig being the standard. If you have an application in production that doesn't need 4 gig, you take a hard look at that application in terms of like, hey, is this even in production like worthy? It might be a very low-key application. It might be an application that's got 5 users. Yeah, in that case, 1 gig is more than enough. Sure. But we're talking about enterprise-grade web apps here, and almost all of them have these type of issues. So the 4 gig is adequate. Now, almost always, this is where the third platform pattern actually gets into trouble, right? And I brought this up recently in a discussion. I said, look, you have category 3, and actually I used to use the term category 3 before platform 3 was even coined out. So there's no direct relationship here. And this is based on what I've seen out in the industry is that you always have on the left-hand side category 1 web apps trying to use category 2, which happen to be either in-memory databases or messaging systems or a combination of the two. And the scaling factor between these two systems is completely different. Every one of you has this platform pattern. And what we've seen today is there's different ways of sizing these. So it's important to keep that in mind. So when what's being talked about is a third platform only world, in other words, only that right-hand side of the slide, is actually not true. It's always a second platform using a third platform. So if you're introducing microservices into your application, guess what? Guess where you're going to start? You're going to start in your middleware services. Those are the easiest to kind of segment out, right? You're not going to go to your monolithic UI WAR file and start chopping it up. Yeah, if you have business logic plugged in there, you might kind of rip that out and separate and so on. But eventually, you still have a monolithic component, and I don't really like that word. That word almost assumes, oh, it's monolithic. That means it's useless. No, I'm sorry. I don't buy that. So you'll find this pattern, and it's important to be cognizant of it and understand it. All right. So I like to call category 3 the golden category. It's a super category in terms of like it fits every enterprise deployment. Category 1 is the most common for web apps. To avoid too many JVMs in category 1, consider minimum 4 GB. Scale up before you scale out. Okay? So if you have deployed an application and it's got scalability issues, don't go asking for an additional JVM. It's not going to fix your problem. Go scale up the heap of the existing JVMs before you scale out. Because scale out costs you money. And it doesn't fix the problem. Yes, it gives you better availability, but your problem, most of you, your problem is not availability these days, it's response time. Okay, let's do this. How many people here think response time is their main problem with their applications? Be honest, okay? Was that like 40%? How many people here think that their availability is availability? In other words, the availability of the total service is a problem. Okay, about 10%. All right. So I wasn't bluffing you. To be honest, and this has been proven out a lot, after n+1, like after 3 copies of a JVM, you really are just wasting money. Okay? Now, you might have legitimate claim to that. You might, and I'm assuming here it's the same application, right? We're talking about the same app here. We're not talking about a tenancy issue. Then, unless you have the concern of very large heap spaces, then you scale out, but really it comes at a cost because, the JVM needs to have a monitoring agent and so on, right? And then the JVM overhead. All right, and Category 2, don't forget, in-memory databases, and there's a specific way of tuning those, right? We talked a little bit about that. I've written a lot more detail, like in terms of specifics, Gemfire, SQLfire, and other in-memory databases in terms of how to actually tune them. Okay, rule number 4, establishing the building block VM. There are really 3, question?
What's the NUMA?
Sorry?
NUMA.
Oh, okay, you saw that on a slide? Where did you see that? Oh, forgot to talk about that. All right, you asked for it, so since this is a developer community, I wasn't going to talk about NUMA, but hey, since there was a question about what NUMA is, we might as well talk about it because it's important for category 2. When you buy a server, there's a reference to sockets, right? And this is not Java.NET sockets. This is not TCP/IP communication. This is actually the CPU die that's sitting on the hardware is called a socket. And it has cores on it. So if I buy a 2-socket server with 16 cores, 8 cores are on one socket and the other 8 cores are on another socket. If I buy this server with about 100 gig worth of RAM, just to do the math simply here, should be like 128, but anyway, the 100 gig RAM will have 50 gig on one socket and the other 50 gig on another socket. So what does that mean? That means if I have a process that needs more than 50 gig, is going to interleave and fetch memory from the remote socket to bring it over. And this becomes a problem with very large processes and in-memory databases and very large JVMs because the act of going to another node and coming back for Java apps is a 30% drop in memory throughput. It's significant. It's funny, when I first got involved with this a few years back, I had done distributed computing for many years, but I had not deeply looked at in-memory databases. The distributed computing guys did not know about NUMA. How can you be in large memory space and in a distributed fashion not know about NUMA? It's astonishing. So it's the single most important thing. So when we size processes, we like to size them to fit within the NUMA node. Okay? Yeah, question?
So the latest tendency is not to buy servers, it's to run a virtualized source.
Yeah.
Will you touch on capacity planning when it comes down to the package solutions you get from AWS?
Okay, so you got to repeat the last part. When you
Will you be touching on capacity planning, in the context of AWS offerings, like when you get a prepackaged VM?
Yeah, okay. So when you get prepackaged, so in other words, you get a prepackaged VM and you don't know what the underlying infrastructure is, right? I'm not going to go into AWS intimately. I've kind of given hints about how you should know what your application uses before you go over there. And really, you need to do a study. But a lot of what I'm focusing on today is trading platforms. And you're not going to run trading platforms on AWS, right? You're going to have your own internal system. But that's not to steer away from the fact that you should be able to say, I'm going to run an in-memory database on this infrastructure provider, in this cloud. I need you to guarantee that latency will not be an issue. Now, they can say it's not an issue. You deploy, and it's going to be an issue. You find that you've exceeded the NUMA boundary. So in your requirements, when you're purchasing the service, you should have in there saying that NUMA boundary should not be exceeded. And that'll be interesting on AWS. I'm not sure how you can do that. Because, so for example, like with the trading platform that I was referring to, their customers are exchanges. So the Mercantile, Chicago Port of Exchange, all of those guys are customers of this trading platform service provider. Their contract says something like this, that your transactional response time to me as the exchange should never fall below a certain response time number, right? If it falls below that response time number, then you pay a penalty. There's a monetary penalty. So not only do they cannot afford to suffer an outage, they can lose their predictable runtime response, response time response. So that sort of requirement is difficult on AWS, right? Can it be done? Probably it can, but it'll be a custom deployment. Now, some PaaS providers will actually let you do a custom deployment, right? I'm not going to get into who does that, who doesn't do that, but some will let you, develop your own deployment packs and say, oh, I want it a certain way, right? No one has deployed a trading platform onto the public cloud yet, right? What's happening in the trading community is they're building their own, so not to mention this customer name, but you could kind of figure it out. They're building their own, so the trading community themselves are building privatized clouds and offering it to the other trading communities within that section of the world. That's what's happening there. But you're right. If I was doing it, I would ask those questions. It is opaque, and it's dangerous to be opaque. It doesn't mean it's, but for web apps, it doesn't matter. Well, 80% of the time, you're going to be deploying web apps. As long as you know your heap space requirement and so on, and most of them, they just ask you for heap space, right? They don't even ask you for CPU. They give you that at the end of the month. So hopefully I answered your question. All right, let's go back to the building block VM. It's also good to establish a building block container or VM and so on for your applications, because the last thing you want is one application having one different size versus other, right? So part of the certification process is I like to certify a VM as the golden template. In other words, I know this application X, I'm going to deploy 2 JVMs or 1 JVM on this OS. I make that decision. I'm going to give it 100 max threads on my Tomcat container, and I'm going to test it out. It's going to have a 4 gig heap and so on. I certify it, and I launch it out. Now, here's where it helps me. When I go to scale it out, I use exactly the same building block to launch other instances. Many times I find a missed deployment as following. Remember, there's 3 instances of this application. These will be members of a pool inside a load balancer, right? So you send equal amount of traffic, right? If this was a 2 vCPU VM, every other container would be of 2 vCPU, and you send equal amount of traffic based on least connection algorithm and so on, right? From the load balancer. Customers get into trouble. There's a response time issue, and then they'll change this CPU to, say, 2 to 4, right? And all of a sudden, they'll say, oh, my load balancer is not distributing correctly. But the actual fact is that they did not tell the load balancer that it needs to be a weighted algorithm distribution, because the middle VM has 2x more CPU processing capacity. All right? Now, I like to keep it simple, keep every VM or container the same amount of CPU utilization, and just scale up. If I have to change the original building block VM, I will go through the effort of changing it for everything. And again, if you apply the original rule where I say before you scale out, try and scale up, that's what I would do. Because scaling up memory, let's say you go from 2 gig to 4 gig, it costs you very minimal on the amount of CPU. I'm going to show you a performance study in terms of what the cost is. Let's go. Running a little behind schedule here. Here's an in-memory database type of setup. This happens to be a 32 gig JVM, but again, everything kind of applies. The only thing you'll notice there, the stack is 1 meg. And typically we do that, we get an additional optimization. There's a specific, I won't go into it, it's more for the infrastructure guys of this world in terms of the cache registers that are on the CPU. But when you increase the stack, I'll explain it. So Java has a thing called escape analysis. So if the objects within a particular thread are not needed by another thread, Java is smart enough to do an inline explosion of the object graph and piggyback on the stack. So when it does that, it actually is populating the register space that's on the chip. This is commonly known as L1, L2, L3 cache that's on the register. It's before it goes into memory. So you'll find in-memory databases benefit hugely from this optimization of increasing the stack from the default 256K to 1 meg, 2 meg, 3 meg, and 4 meg. Now remember, this is per thread, so you're gonna chew up memory pretty quickly. Oh, let me skip over that. I actually explained it. Let me skip over this. All right. So this is a common question. I have an application I'm trying to deploy. It could be a PaaS, so back to your AWS question, right? And I have a decision to make. Do I deploy 4 JVMs of 1 gig each, or do I deploy 2 JVMs of 2 gig each? Usually I ask, what do you guys think? But I think you've already seen the answer. So it turns out that scenario 2 of 2 JVMs of 2 gig heap each performs 26% better in terms of response time. That's kind of okay. It's only 26%, right? Here's the shocker. Scenario 2 uses 60% less CPU. So I'm not saying let's give up on scale out and end what we've known about computing in the last 20, 30 years. I'm not saying that. What this proves is that if I have a system that has been proven to need 100 JVMs, I'm willing to challenge that thinking. Because I could probably run it in 25 JVMs. Okay? Now, when I did this test, I promised I would not tune in my favor. And I was very honest. I did not tune in my favor. I kept everything default. This was a complete default setup. The only thing I could control was the amount of heap, the max heap setting. And this was the result. And you can repeat this over and over again. And please try it out in your own time and message me back and tell me that I was completely wrong. I don't think that'll be the case because we've tried it so many different times over and over again. This is the single biggest myth that exists in the developer community and the Java community, that if I had not shown you the results, almost everybody here would say, of course 4 JVMs would be better than the 2 JVMs. And the reason being is because when you get rid of 2 JVMs, there's 2 GC cycles, heavy cycles you just got rid of. Sorry, there's a question here. Yeah, so the question was, when I claimed this to be default, what GC is the default GC? So it's the throughput collector. Yeah, it was really default. I didn't mess with it, so. Now, there are times where you'll find you're quickly trying to release an application, and you happen to put the job scheduler in the same JVM as the web application. You know, the scalability paradigm of the web app, you know, is one way, and the scalability of the job scheduler is another. So job schedulers will care about memory throughput. They want to push as many big objects through as possible. There's not a user sitting there waiting for the button. It's not like in a web app. You know, you're trying to put in as many users as possible through, and so on. So over time, you end up in this compromised state. What I like to do is separate those concerns out. So put your job schedulers, you know, like a batch systems, onto a set of JVMs that are specialized in that. And the way you size them and scale them is different. And in terms of web apps, you put them in their own JVMs. So keep that in mind. Java, you know, I like these guys who always come up with stuff to stigmatize it and make it look bad, monolithic, legacy, and so on. And somebody told me the other day, Java's legacy. I said, well, the language has kind of moved on and morphed itself, right? Other flavors. But the JVM lives on. And the reason why the JVM lives on is because it's a 64-bit kernel. The theoretical limit of the kernel is 16 exabytes. You can fit this entire world into a single JVM. But there's not a single OS in the world that can give you that much contiguous memory. So the OS limit is a concern. And then if you're using virtualization, that's another limitation. But the real limitation is the physical NUMA memory that's available on the box. That's the real limitation if you care about performance. Because if you exceed the NUMA boundary, you'll suffer 30 to 50% in drop in memory throughput. So the Java virtual machine will be with us for many years to come. It will not go anywhere, not Golang, right? I'm not going to pick on Go because we recently did a study on Go and we beat it by 5x. Java just hands down beat it. It's got its own specific uses and so on, but for all the Golang guys, you know, just yeah, you can follow up with me. Okay, let's skip over that. I want to get to this section. I really want to cover this section today. So whenever I get into a situation, I really don't give up. And remember, one of the rules was that when you fix a problem in one tier, you've just shifted it to another tier. That always makes you sleep less at nighttime. So I like this quote from Einstein. You know, Einstein was just really efficient. It was all about efficiency. You know, we say he was a really smart guy, and he was very intelligent, but he used efficiency and persistence to actually go after a problem. And let me just skip over that. So when it gets to tuning, the Java world is kind of split between two chasms, right? This is really the GC algorithms. They're either designed to reduce latency, or they're designed to increase throughput. It's one at the cost of the other. Now, I'm going to go through, I'm going to show you a configuration that uses a compromise between the two that gets you pretty close to the green line over here. Now, so for many years, this configuration was private to VMware. We actually had experimented with it and so on. We had kind of held it close to our chest. But about, I think, 2.5, 3 years ago, we decided, you know what, let the public have it, right? And this configuration has been tried and tested. The largest JVM that I tested on was a monitoring system that did not scale out, not to pick on the vendor. It was a 360 gig JVM, single JVM, 360 gig. And it works on it. So when we talk about, you know, reduced latency and latency sensitive, your web apps are latency sensitive. Your batch and job schedulers are, you know, throughput bound, and your in-memory databases are latency sensitive. So before we go into the algorithm, let's look inside the JVM heap space. So what happens is we have the Eden space where objects are created, and there's two survivor spaces. Young generation minus XMN is a thing I love to use, and it's absolute. It's not using new ratio. I don't like variable things. I like to predict the future. So don't use new ratio. Anyone tells you use it, shoot me an email. I'll explain why not. And typically you'll find minus XMN is about anywhere between 10% to 33% of the heap space. Do not exceed 33%. You'll get into trouble in terms of early tenuership. So what happens here is all objects are created in Eden space, right? And after some time, some objects will die. There's a thing called quick minor GC that will happen. It'll take them out. But the ones that survive will go to the first survivor space. Then after a while, you know, they survive again and go to the next survivor space. There's a little, you know, optimization hack in there. They actually don't copy them. They flip the survivor space names and so on. Anyway, but the cost is not huge in terms of that copy. It's a reference movement. After some time, there's a much slower process called promotion, tenuireship, right? From young generation to old generation. And that's costly. Over time, things build up. You get full, slower GC, and takes them out. Notice there's no specific way to tune the old generation. It's implicit. So in other words, if you set the young generation and you set minus XMX, what's left over is the old generation. So putting it all together is what it looks like. On the left-hand side, we talked about the memory space, the heap and off the heap, and this right-hand side chart is what's inside the heap. Okay, so here's the golden configuration that we had kept as a secret and released it 2.5 years ago. I'm going to use a par new GC and a parallel GC threads for young generation. So I'm going to use 2 different GCs, okay, side by side. Par new GC is parallel new garbage collection, and parallel GC threads controls the number of garbage collector threads. It's basically serial, but made scalable by having multiple threads. So when it runs, it still stops the world, but it at least has multiple threads kind of running and cleaning. On the right-hand side, I have the concurrent marking suite, the CMS. And it's concurrent, meaning it runs along your application threads. When it runs, it does not stop your application threads. Now, if there was a JVM engineer in here, it was like, oh, wait a minute, it does actually have 2 short pauses. Yes, it does, but they're insignificant. So this is what some of them, the purists, will say. It's mostly concurrent. But it's much more concurrent than the parallel throughput collector that's in the young generation. And so what we do is, when we're doing the tuning, we look at the minor GC threads. We're going to kind of inspect that frequency, and I'm typically trying to get rid of an additional frequency so I can create space for my application threads to run in here. And same thing in the all generation. So I actually have a recipe for this. First, what I do is I measure the GC duration, which is the width of, when a GC runs, how long does it take, and the frequency, how many of those we're getting. And then based on that, I'll adjust minus XMN. The only thing you can do is adjust minus XMN or parallel GC threads, okay? Now, once I'm done, let me go back one step. Once I'm done with young generation tuning, I'll move on to old generation tuning. And again, I'll measure the GC cycle there, and I'll measure the frequency and so on. The only thing you can do to affect that is minus XMX adjustment. Either reduce it or increase it. Now, step A and step B applies to category 1 and category 2. Okay? Now, step C is a refinement step. You seldom have to worry about it if you're dealing with web apps. If you have a survivor ratio of somewhere between 6 to 8, you're good. You never have to touch survivor spaces. But in in-memory database space, if you're dealing with a 90 gig type of heap space, your survivor spaces may be, 5 gig, 10 gig, and so on. It's a significant amount of memory. So this is where we will play around with the survivor ratio. Okay, let me just actually look at an example. So what happens when I increase young generation? Let's say I increase it by 10%. Here I have a situation where there's a frequency here in the middle. I just got rid of it. The reason why I want to get rid of it is because I want to fit as many application threads in here as possible. Okay? Now, what's the downside of that tuning? The downside of that tuning is that those 2 frequencies of minor GC that are left over take a little bit longer to run now. Okay? And the other downside is that since I increased young generation by 10%, I took that 10% away from the old generation. So I made old generation a little bit smaller. So the downside of doing that is I may get an additional full GC in here. Now, I may not care about that too much because I got plenty time in old generation because these frequencies may happen hours apart. But over here, I care about the space because these are seconds apart. Now, one thing you can do to fix these two problems is in young generation, when the width has increased, you can increase the number of parallel GC threads so you can actually do the clean out quicker and reduce the pause. Now, when I'm actually setting the configuration for parallel GC threads, I start at 50%. So in other words, if I have 8 vCPUs or I have 8 CPUs, 4 CPUs will be allocated to the parallel GC threads. Now, the reason why I do that is because there's a bug. Well, I think this is a feature. Not to sound like a cliche, but in a JVM, if you deploy on an OS and it sees there's 8 vCPUs, it takes all of those 8 vCPUs and allocates them to the parallel GC threads. So in other words, it says the JVM is a first-class citizen, there's nothing else running on the OS, and during this GC cycle, I'm going to take up all the CPUs. That's not true, right? Here's the other thing that I never quite understood. If you have, let's say, 12 vCPUs, beyond 8 vCPUs, the calculation is 5/8. So about 50% of those 12 vCPUs will be allocated. So why is it 8 vCPUs and all of a sudden it drops to 50% after 8? It kind of doesn't make sense. So the good practice there is always set it to 50% and then run your workloads and so on. And if you've got plenty CPU and you still want to improve your response time, keep increasing parallel GC threads one thread at a time. One thread at a time. Those are heavy threads. So that's what I do, kind of fix that problem. Now, to fix the full GC problem where we introduced a new GC here, you just increase minus XMX by 10%. Because you increased minus XMN, young generation, by 10%, it's a sliding window, you just increase minus XMX by 10%. Or you may choose to say, it doesn't bother me. It happens every hour, I don't really care. In some cases, with New Edge's trading platform, their GC in old generation runs for 12 seconds, and it happens like once every 6 to 8 hours. We make sure we've deferred it so far out that it skips over the peak of traffic. Now, what happens when you reduce young generation? You've just made Eden space smaller. So you're going to get an increased frequency of young generation. Now, why would you want to be doing that? This is actually an exception rather than the rule. Sometimes with in-memory databases, you have such a large heap space is that you don't need 30 gig young generation. And the downside of actually reducing it is you've just made the old generation much larger, right? So the full GCs will take longer to run. And you have to fix that by adjusting minus XMX down. Now, survivor spaces are calculated as an inverse ratio. Basically, the survivor space size is young generation over the ratio +2. The +2 is there because there's 2 survivor spaces. All right, let's see. I got about 6 minutes. Let me just quickly go over something here. Okay. I recently got engaged with a tuning of a platform. It had 25 unique REST services deployed out. On day 1, they had basically 1 gig JVMs mapped to 1 REST service. I mean, everywhere you read, unless you go to my blog on vmjava.com, I have a blog that talks about practical microservices. where you don't need to have a mapping of one microservice to one JVM. Anyhow, and in this particular case, they had about 16 physical hosts. They had 25 JVMs on day one, and over a period of time ended up with 400 JVMs. So every time they needed to scale out, they scaled up by another 25 JVMs because the full functionality required the 25 REST services and so on. When I inspected the system, I went to the load balancer, started doing, actually walked through the transactions and looked at the logs. I found that every time there was a transaction between the first REST service, it traversed all of the REST services and back, all of the microservices, and almost 90+% of their transactions. So they were impacted by a huge amount of network hop. So let's look at it. This is what it looked like. So they had a load balancer. They had 25 JVMs basically on the server. And you get a REST call to the first REST service, then back to the load balancer, and then it eventually goes to the 25th to complete the transaction and back. Now, the next one comes along. If it's not lucky, it'll go on another server because R25 on server 2 responded, right? It go load balance, then it responded. So all day they were suffering from this. Now, using NUMA optimization, we can just shift, lift and shift, put 50 JVMs and 2 VMs. That's kind of interesting, but it doesn't fix the response time problem. You end up with half amount of the hardware, right? But still the response time is a huge, huge problem. So again, the response time doesn't change because the load balancer is like this. So let me just skip over this. So what's the solution? So what I did was I took the 25 REST services and I put them all into one JVM. They immediately told me you're not allowed to change any code. I begged for changing just one configuration file. Instead of pointing to a VIP, I pointed to a local host. And I put all of the 25 REST services within one JVM, so it goes back like that. Versus what it was like this. Okay? The improvement was 3x better response time right off the bat. Okay? So what I'd like to think, if you look at what I did was, basically you have 25 REST services inside one memory space. Now you still incur the overhead of the marshalling and unmarshalling of the protocol, but that's not as significant as the network hop, the 25 network hops that we just got rid of per transaction. So anyway, the old system used to run in 16 hosts. The new system runs in 6 hosts. And for the next year, they wanted to double in traffic. They went back to 12 hosts. So think about this. 16 hosts down to 6. And 3x better response time. Oh, yeah. So actually, that's a good question. So I think what you're saying is when you consolidate a macro deployment like this, how do you track where is the bad code? Actually, we didn't change the method call paradigm. I mean, all of the method interfaces were the same, and they had actual traps in terms of the start and end of the method. So all of that did not change. So they knew exactly where the objects were being created, by which method. All of that did not change. So they had instrumentation on all of the method calls. Yeah. So that was the saving, 62% saving in terms of hardware and licensing costs. There was a monitoring agent that we're using. Every monitoring agent was $2,000 a JVM. So they got rid of, majority of that. Let me just skip over to this notion. How much time do we have? We got 1 minute. Let me cover this. So what we're really talking about here is you have to acknowledge that with microservices, you're going to have a fan out of services, right? You can continue to micro-define. On the left-hand side, this customer had micro-defined and micro-deployed because they had a one-to-one relationship between a JVM and a microservice. An improved state would be you can continue to micro-define, but macro-deploy. Not monolithic deploy, okay? You can't call it that. So, and this gives you the benefit. And there's really a lot of work being done in this area with Mesos, Kubernetes, and Microservices Manager that we're working on about scheduling these services. Day one is all about the packaging and the deployment of these things, but day two is about the interaction and management of the interaction. Okay. Any questions? I know I didn't leave time for questions, but yeah, go ahead.
One JVM has 25 services. One Tomcat use, the other use case?
Yeah, there's 25 WAR files, REST WAR files, into one Tomcat instance, and then we just scale out the Tomcat instances like that. Yeah. Sorry? Oh, what's my blog? VMJava.com. VMJava.com. All right. Any other questions? All right. Yeah. Yeah. Oh, to be what? No. You can. You'd have to use NumaCTL at the Linux OS. Yeah. All right. Thank you.